Okay, let's walk through each of these. So, like I usually do, I am skipping this paragraph. I'll go back to it if I need it. Right down to the question, it says, which of the following was true for the system between time 1 and time 2? And then when I come over here and I look at time 1 and I see time 2, I see that the concentrations have leveled out. They stopped going up and they stopped going down. That means starting at time 1, we've reached equilibrium. Okay? So answer option A says the concentration of N2 decreased. No. The number of effective collisions between H2 and N2 is 0. No. The rate of the forward and reverse reactions are equal. Yes, because that's one of those things that happens at equilibrium. Only when we reach equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Now, number 2. As the reaction progresses towards equilibrium, the rate of the forward reaction... Okay. Now let's think about this for a second. Here's a rate versus time graph. And if we started with only reactants, and I don't know if we did, but we're going to assume because it hasn't said otherwise, then the forward rate starts off way higher than the reverse rate. However, it's going to decrease and the reverse rate is going to increase until they equal each other. And that's when equilibrium is established. So here's my forward rate, here's my reverse rate. And so as the reaction progresses towards equilibrium, the rate of the forward reaction, see how it is higher than the reverse reaction, but it's not increasing, it's decreasing to become a constant non-zero rate at equilibrium. It becomes a constant, it's not going up or down, but it's not zero, it's not down here. So the answer is C. Okay, number 3. Again, we got a little paragraph here. I jumped in the end because I want to know what I'm needing. I'll go back and read it if I need to. Which of the following best predicts whether or not the system has reached equilibrium at 300 seconds? And then we do need a little bit here because I don't know if these are reactants or products or what. So equal molar mixture of X and Y is placed inside the rigid container. Okay. So I think I can reasonably assume that X and Y are reactants, and then I see this XY combo, which is probably the product. So X, Y, and then XY. So the amount of X that we have, 1, 2, 3, 4, 5, 6, 7, and the amount of Y, also 7. And then see this XY combo, we don't have any of those yet. Now this is what I'm going to tell you. I'm going to write numbers above all these other ones, but I'm going to write the amount of X, the amount of Y, and then the amount of XY. So then for time 100 seconds, there is 1, 2, 6 X, 1, 2, 4, 5, 6 Y, and then 1 of those XY combos. And then time 200, we have 1, 2, 3, 4 of the X items, 1, 2, 3, 4 of the Y items, and 1, 2, 3 of the XY, and then it looks like we have 2 of the X's, 2 of the Y's, and 1, 2, and 5 of the XY. It never stabilized, right? The amount of reactants was going down, the amount of products were going up, but then it didn't ever level off. The concentration or the amount kept changing, so I'd say that it has not reached equilibrium yet. So then looking at my answer options, A, it is not possible to determine that the system has reached equilibrium. No, it is, or we determine that it has not. It's not possible to determine the system has reached equilibrium. I don't love that one. The system has reached equilibrium. Okay, let's reread. So I think we determined that it's not, but we know that sometimes answer options are weird. So it is not possible to determine that the system has reached equilibrium by 300 seconds because the stoichiometry of the reaction is not known. It is not possible to determine that the system has reached equilibrium by 300 seconds because the amount of x, y have continued to change. That one feels the most correct to me. And then C and D I know are not true because it says the system has reached equilibrium, and it has not. Has reached equilibrium. Okay, so number 3, B. On to number 4. Now, again, we got a little paragraph of info here, but I want to know what I'm doing. What am I solving for? What is the value of Kp? All right, now, anytime they're asking you to solve for a K value, whether it's a Kp or a Kc, we need an ICE table. And then once we have that ICE table, then we need to plug in info from it into our K expression. That's the steps here. So I'm going to set up the ICE table. COCl2 turns into COCl2. They're all gases, so I'm going to include all of them in my ICE table. If they're a gas or aqueous, then we're good. Okay. Now that I recognize that, I am going to go back to the beginning and read the whole thing. So COCl2 decomposes according to the equation above. When pure COCl2 is injected into a rigid previously evacuated flask at 690 Kelvin, the pressure in the flask is initially 1 atmosphere. So initially we have a pressure of 1 atmosphere. Now just a reminder, pressures and concentrations, those can go on ICE tables, not moles. Moles are BCCA table. So it was previously evacuated, there was nothing in there, we only put COCl2 and the pressure was this. And so like we typically see, the amount of product initially is 0. Now whenever it's a reactant, it's going to be a minus, and whenever it's a product, it's going to be a plus. And the coefficients in the front of these items tell us by how much. So because there's a 1 here, this is just going to be minus x. Because there's 1s in each of those, they're both going to be x's instead of like a 2x or a 3x. So at equilibrium, we'll have 1 minus x, we'll have x, and we'll have x. Now, it goes on to say, after the reaction reaches equilibrium, the total pressure in the flask is 1.2. Now, at equilibrium, this guy is present, and that guy is present. Like this 1 minus x plus x plus x. All 3 of those are present, and if we add them together, it should equal 1.2 atmospheres. Now, see this minus x and this plus x? Those cancel. Like what we're left with is 1 plus x equals 1.2, and so then that means that x is just equal to 0.2. And if x is 0.2, then 1 minus 0.2 is going to be 0.8 atmospheres. X is 0.2, and x is 0.2. So there's the info from our ICE table, and we need to plug it into our K expression. This time it was a Kp. So products over reactants. Here's my pressure of CO, pressure of Cl2 over pressure of COCl2. All of them are raised to the first because they had coefficients of 1 in the balanced equation. And then we know what those items are now. So then this is going to be 0.2 times by 0.2 divided by 0.8. 0.2 times by 0.2 divided by 0.8. And we get an answer of 0.05, and that's why our answer is B. Okay, on to number 5. Again, I jumped to the last sentence. What is the value of Kc? Okay, so we're solving for a K expression, so we need an ice table, then we need to take info from the ice table and put it into our K expression. 2NO2 results in N2O4. They're both gases, so I'll include both of these in my ice table. And then I'm going to start reading the paragraph because I'm realizing I probably need info from it to fill in this ice table. The dimerization of nitrogen dioxide is an exothermic process represented by the equation above. A 0.03 mole sample of nitrogen dioxide is placed in a rigid 1 liter reaction vessel. Now remember, we talked about this. We're not going to have moles in an ice table, only in a BCCA table. But they give us the amount of moles and they give us the amount of liters, and concentration is moles per liter. So if I have 0.03 moles divided by 1 liter, that means that the concentration of nitrogen dioxide is 0.03 molarity. And nothing else was present in there, so like usual, we start off initially with 0 product. Now, reactants are a minus, products are a plus. So at equilibrium, we have 0.03 minus something and then 0 plus something. Now, the coefficient right here is a 2, so this is not just minus x, it's minus 2x. And then the coefficient for our product is just a 1, so it's going to be plus x. And we know that 0 plus x is just x. Okay, now I'll keep reading. So a reaction vessel is allowed to reach equilibrium at a certain temperature. What is the Kc at this temperature if 0.005 moles of N2O4 is present at equilibrium? Again, this 0.005 moles is in a 1 liter container. So at equilibrium, the concentration of N2O4 is equal to 0.005 molarity. Well, this is good because now we know what x is equal to. X is equal to 0.005. So then I could plug it in right there. I could do 0.03 minus 2 times by 0.005, which will just equal 0.02. So now that I've gotten my values from my ice table, I need to plug it into my K expression. Now this time it was a Kc, so I'm doing concentration. And it's products over reactants. So here's my product, here's my reactant. However, nitrogen dioxide has a coefficient of 2 in front of it, so this guy needs to be squared. So Kc is going to equal 0.005 divided by 0.02 squared. 0.005 divided by 0.02 squared, 12.5. So then our answer is D. Okay, now reminder, Le Chatelier's principle is a reaction responding to a stress, okay, throwing it out of equilibrium. And we're figuring out how it's getting back to equilibrium. So again, I'm going to skip to the last sentence. It says, which of the following best describes what will happen to a reaction immediately after additional iodine gas is added? Now, reminder, when I analyze these, I draw arrows up above the reaction to represent the stress, and then how the reaction responds is the arrows down below. So immediately after the addition of iodine gas. So this stress is going to be adding iodine gas. Now the reaction responds, by trying to decrease the iodine gas. And the only way that we can decrease a reactant is by favoring the forward reaction. This is when reactants are turning into products. So all of our reactants will decrease and our products will increase. Now, before I look at answer options, here's a couple things that we could say. We could say that we are going to favor the forward reaction. We could say the rate of the forward reaction will be greater than the rate of the reverse reaction. We could say that the concentration of H2 will decrease. We could say that the concentration of HI will increase. Pressure, we probably don't see much difference, if any, because do you see how there's two gas particles on the reactant side, but then there's actually two gas particles on the product side? So favoring the forward really isn't going to make the pressure go up or go down. So now let's see what our answer options say. The rate of both the forward and reverse reaction decreases. No. The rate of both the forward and reverse reactions do not change. No, they do change. The rate of the forward reaction becomes greater than the rate of the reverse. Yes. Favoring the forward reaction. Okay. Number 7 says, which of the following was true for the system between time 1 and time 2? So if we look at time 1 and time 2, we recognize that the concentrations have stopped changing. They've stopped going up and down, so we've reached equilibrium. You've seen this one. Didn't we do this one already? Yeah. Look, it's the same. Sorry, y'all. Put it on there twice. The rate of the forward reaction and reverse reactions were equal. Okay. I thought that was it. There was another question that said after time 2, they did something to it, like they added a stress, and that's the question I thought I copied over, so my bad. Number 8. A 2 mole sample of carbon monoxide and a 2 mole sample of water are introduced into a previously evacuated 100-liter rigid container, and the temperature is held constant as the reaction represented above reaches equilibrium. Which of the following is true at equilibrium? If they're asking you, hey, what's going on at equilibrium? Like, what are the amounts or comparative things at equilibrium? We need an ice table, because an ice table is a great way of seeing what's happening for a reaction at equilibrium. So we have CO plus H2O results in CO2 and H2. They're all gases, so I'll include all of them in my ice table. Okay, now 2 mole sample of CO, but only concentrations or pressures in an ice table. So it's 2 moles in a 100-liter reaction vessel, right? 2 moles per 100 liters, so the concentration is 0.02. Same with this guy, 0.02. 2 mole sample of carbon monoxide and a 2 mole sample of water are introduced into a previously evacuated 100-liter rigid container. So our products initially are 0. Now, reactants are a minus, products are a plus, and then hello. Sorry to bug you. No, you're good. I'm just getting a video ready for my kiddos. So reactants are a minus, products are a plus, and all these have coefficients of 1 in the front. So this would be minus x, and these would be plus x. So we have 0.02 minus x, 0.02 minus x, and then 0 plus x would just be x and x. Okay, nice. Now, hey, other thing, notice Kc is a relatively large number. And so when K values are big, because Ks are always products over reactants. So when this is a big number, that means that there's more products and less reactants, right? So here's our products. And so there must be more of these guys and less of those ones. Okay, let's look at our answer options. So let's see. A says that water is going to be larger than carbon monoxide, but no, they're going to be equal. So answer option A is not it. Now let's see. Water is larger than H2. And so let's check that one. This one's going to be less, that one's going to be more. So that's the opposite of what B says. And then here's carbon dioxide, and here's carbon monoxide. And it's saying this one's bigger than that one. That's true because of this. So C is good. And then they're not all equal to each other. These are equal, but they're not equal to each other. Great. Okay, number 9. I think I'm going to put delta H's in here as well, because that's what's commonly forgotten, is how to deal with delta H compared to K values. So we have reaction 1, reaction 2, and we're trying to figure out the K value of reaction 3. First thing I'm noticing, there's 1 mole of CH4 on the reactant side. However, for reaction 1, we do have 1 mole of CH4, but it's on the product side. So I need to take reaction 1 and I need to flip it. I need to have CH4 plus H2O results in CO and 3H2. And here's how K values are different than delta H's. Because we flipped this reaction, I'm going to do 1 over K1. And because I flipped this reaction, it would be a negative delta H1. Now I see that there's 2 water molecules. Here's one of the water molecules. Here's another water molecule. So if we flip reaction 2, that would give us 2 water molecules. Let's double check. And yeah, look, see how we have CO2 on the product side, but it's on the reactant side for reaction 2? So let's also flip reaction 2. So that would mean we'd have CO plus H2O turns into CO2 and H2. Okay, so then because we flipped the reaction, we're going to do 1 over K2, or a negative delta H2. And then this gives us what we would hope, that the carbon monoxide cancels, and we're left with CH4 plus 2 H2Os, resulting in a CO2 and 4H2. And that's what we get for reaction number 3, which is great. Now the difference between our Ks and our delta H's is this K3, we don't add them, we multiply them. So here's the inverse, here's the inverse. So we wouldn't add these, we would multiply them. So it'd be 1 over K1 multiplied by 1 over K2, like that. Now, if it was a delta H3, then we would add them. We would take this negative delta H1 and we would add it to the negative delta H2. So the answer then is D. Oh, yeah, because it's multiplied. So the inverse of K1, the inverse of K2 multiplied together. For number 10, at a certain temperature, the value of the equilibrium constant K of the reaction represented above is that number. What is the value of K for the reverse reaction of the same temperature? All right, so if we just take the reverse of this, well, I'm going to call this reaction 1, and the reverse will be reaction 2. So K2 would equal 1 over K1. And we know that K1 is 2 times by 10 to the 5th. All right, so 1 divided by 2 by 10 to the 5th, and that equals 5 times by 10 to the negative 6. Okay, nice. All right. Next. K versus Q. So right away, what's catching my eye is these answer options are showing comparing Q and comparing K, and we are given the K, so I bet we have to figure out what Q is. Now a reminder, a Q expression is the same as a K expression, where we do products over reactants. Where this is a Kp, I'm going to go with a Qp, which is pressure. So this would be pressure of CO2, pressure of H2, divided by pressure of H2O, pressure of CO. All of them have coefficients of 1, so they're all raised to the first power. Now the only difference between K and Q is for a K value, these are the pressures at equilibrium, but for a Q value, it's the pressures at any given point in time. So a vessel initially contains water at a partial pressure of 0.3 atmospheres, carbon monoxide as a pressure of 0.1 atmospheres, carbon dioxide at a pressure of 1.5 atmospheres, and then H2 at a partial pressure of 10 atmospheres. All right, so 1.5 times by 10 divided by 0.3 times by 0.1. This equaled 500. Now the next part of this K versus Q, like solve for Q and then determine direction. And what I mean by this is put the K on the number line and then figure out if Q is above or below it, right? So what we have is K, which is 136, but my Q is above that, it's 500. So I need to favor the reverse reaction to get back to equilibrium. Now a couple things during a reverse reaction. Products go down and reactants go up. The rate of the reverse reaction is greater than the rate of the forward reaction. The pressure doesn't change for this guy, because you see how we have 2 gas particles on the right side and 2 gas particles on the product side. So even though we're favoring the reverse, because the gas particles are equal on both sides, the pressure wouldn't change. So let's see answer options, what we have here. We've narrowed it down to A or C because Q is larger than K. Answer option A says the partial pressure of H2O and CO increases. Let's see, H2O and CO increases, yeah. Right. Okay, A. Okay, so for 12, for the system represented above, the concentrations of these guys are initially that and that. Which of the following predicts what will occur as the system approaches equilibrium? And then I'm noticing something that we get these Q's and these K's. So I'm going to solve for Q so I can compare it to my K value here. And we would have concentration of O3 over concentration of O2, products over reactants. But the O3 has a coefficient of 2 and the O2 has a coefficient of 3. So we raise it to the second and the third. Now, the difference between K expressions and Q expressions is for Q, these are the concentrations at any given point in time. So this would be 0.150, and this one would be 2.5. But we can't forget that we need to cube and square this. So 2.5 squared divided by 0.15 cubed. Now, here's my number for Q, but look at how teeny tiny my K value is. So I'm getting a much bigger Q than K, so we're going to be favoring the reverse reaction. So a couple things with this. If we're favoring the reverse reaction, that means the rate of the reverse will be greater than the rate of the forward. It also means that the concentration or the amount of my products are going down and my reactants are going up. Also something with pressure. See how we have 3 gas particles that are turning into just 2 gas particles? 3 gas, 2 gas, and we're favoring the direction of 3 gas instead of 2, the overall pressure would increase. Now, looking at these answer options, we can narrow it down to C or D because this is where Q is bigger than K, and then C says the amount of O3 will increase. No, see, here's O3 and it's decreasing. Answer option D says the amount of O3 will decrease, and we go, yeah, that's it. Okay, 13. Before I dive into it, I'm noticing that I have a positive delta H, so that would mean that it's endothermic, so I'm going to write heat on the reactant side instead of the product side. And then the question is, which of the following changes will increase the amount of barium dioxide? So we want the reaction to respond by increasing the amount of barium dioxide. Now, the only way that we're going to increase a reactant is by favoring the reverse reaction. And during a reverse reaction, the products go down and the reactants go up. So we have a couple different ways of doing this. One thing that we could do is we could add gas, add O2. That would cause this favoring of the reverse reaction to occur. I would not increase the concentration of barium oxide because it's a solid, and we can't do that with solids or liquids. Barium dioxide, again, this is the item in question, so I wouldn't worry about it, but also it's a solid. Temperature-wise, though, we could decrease the temperature, and this would cause the same thing. So we could either increase the amount of O2 or we could decrease the temperature. There's also something we could do pressure-wise. Do you see how on the reactant side we have 0 gas particles, and on the product side we have 1 gas particle? And we want this to favor the reverse. We want the reaction to respond by turning 1 gas particle into 0, which would be a decrease in pressure. So something we could do as a stress is we could increase pressure, and that would cause this response that we're hoping for. So answer option A says remove, here's the potential stressors, removes a small amount of O2. No, we want to increase the amount of O2. Remove a small amount of barium oxide. No, it's a solid. Not dealing with that. Add helium gas to the vessel. Anytime you add a noble gas, it doesn't change anything. It doesn't throw off the equilibrium. And then the last one is lower the temperature. Yes, if we lower the temperature, the reaction responds by trying to increase it, which does cause us to favor the reverse reaction. Okay, 14. Which of the following changes will increase the amount of NO2? So we want the reaction to respond by increasing NO2. NO2 is a product, so we're going to favor the forward reaction because that's when reactants decrease and products increase. It doesn't tell us if it's endothermic or exothermic. And then notice that there's 2 gas particles on the reactant side and there's 2 gas particles on the product side, and so no pressure change will cause a shift in equilibrium. We don't increase or decrease the pressure by favoring a forward or reverse reaction. So potential stresses would include decreasing the amount of CO. That would work because this is a gas. I'm not going to really worry about the NO2 because this is the item in question that we're trying to increase. We could increase the amount of carbon dioxide. That would work. Or we could increase the amount of nitrogen monoxide. That would also work because those are gases. So let's see what answer options they give us. Remove CO gas from the system. Yes. Remove CO2. No, we want to increase CO2. Increase the volume. Oh, see, if we increase the volume, that would decrease the pressure. And if we decrease the volume, that would increase the pressure. And we don't have any pressure advantages here because it's 2 gas particles on both sides. And so as we saw, A is the correct answer. Now, on to number 15. Which of the following best predicts how the partial pressure of the reacting species will be affected if a small amount of a noble gas is added to the equilibrium mixture? Adding a noble gas makes no change. They really try to throw you off with this. So if we add noble gas, no change occurs. Molar solubility. Okay. What is the molar solubility in water of silver chromate? So silver chromate, Ag2CrO4, solid, breaking apart into these ions. We get 2 of these silver ions and chromate, CrO4, 2 minus. We get 1 of those. Okay. Now, just a reminder, we can, when there's a coefficient of 2 in the front, you can replace the concentration of that particular ion as 2S, or 2 times the molar solubility. And then there's a coefficient of 1, you can just say that the concentration is S. It's just the molar solubility. And this is what we're trying to solve for, is molar solubility. Whenever there's a ratio of 2 cations to 1 anion, or 1 cation to 2 anions, the KSP will always end up being 4S cubed. If we don't remember this, that's okay. You just need to plug it into your K expression, where we do products over reactants, and this would be silver, but it's a 2 because of the coefficient of 2, and then chromate, CrO4. And if you put 2S right here and it gets squared, and you put S right here, this is what you end up with. Now we are given the value of KSP. We know this number. We're solving for S. So my last step is going to be taking that KSP, dividing it by 4. That's going to equal S cubed. So then if I take the cubed root, that's going to equal S. Okay, now I'm KSP divided by 4. So here's my KSP, 8 times by 10 raised to the negative 12. And then I'm going to divide that by 4. And so there's inside of that cubed root, that's what I would get, but then I do the cubed root of that number. However, I'm looking at my answer options here. 2 times by 10 to the negative 12, 2 times by 10 to the negative 12, and then I take the cube root of that. So our answer is D. The value of KSP for lead fluoride is that the concentration of lead in the saturated solution is approximately, okay. We get the same thing. See how there's going to be 1 cation and 2 anions? And so that means the KSP is equal to 4s cubed. Now recognizing which one is 1 and which one is 2 is important though, because the concentration of lead, the thing that we're looking for, there's 1 lead. So it's going to equal S, where if we were looking for the concentration of fluorine, it wouldn't equal S, it'd equal 2S. So I'm going to take this, I'm going to rearrange it and solve for S. KSP divided by 4, cubed root of that is equal to S. And then the good news is that's what we want because that equals the concentration of lead. So KSP is 2.3 times by 10 raised to the negative 8. I'm going to divide that by 4. But then I need to take the cubed root of this. Reminder that the cubed root is the same as raising it to the 1/3. And so S is equal to 0.002 molarity, which is the concentration of lead. 1, 2, 3, so it would be this guy. Okay. Nice. 18. Equal molar samples of lead hydroxide, lead iodide, and oh my goodness, I'm doing what I tell you not to do, which is like reading from the top of the paragraph. Nay, let's jump down to the bottom. Based on the KSP value for the compounds listed in the table above, a solution of which of the following compound will have the lowest concentration of lead? Guys, remember K expressions. It's always with these things that are dissolving in water, it's always the concentration of these ions raised to some order, some number, right? But the important thing here is recognizing that concentrations in KSP are directly proportional. That when we have a big KSP, then we have a high concentration of the ions. Or if we have a small KSP, we have a small concentration of ions. So if we want to figure out which one has the lowest concentration, well then it's gonna be the one with the smallest KSP. So that's why A is our correct answer. Now looking at 19, the question is which of the following is true, and it looks like they're all talking about these concentrations of silver. And then it says beaker X contains 50 milliliters of distilled water and beaker Y contains 100 milliliters of 1 molar sodium chloride. Solid silver chloride is added to each beaker. After thoroughly stirring the contents of the beaker, some solid silver chloride remains at the bottom. If there's solid silver chloride on the bottom, it means that they're both saturated solutions. As much of the silver chloride that can dissolve is dissolved. So let's say this is silver chloride, right? This is our AgCl right in there. Let's say that one of those Ags breaks off from the Cl minus, it dissolves in the water. Maybe it happens again. We have another Ag and Cl, they break apart. But let's assume, let's guess that that's maximum saturation. No more saturation can occur. Okay, now let's look at this guy. Now, a reminder though that this wasn't pure water. This had sodium chloride. That means that there's sodium ions floating around in there and there's chlorine ions floating around in there. Now, I don't really care about the sodium because it's not a common ion. Silver chloride has silver and chlorine, and sodium chloride has sodium and chlorine. Those are the common ions, the chlorine. So I'm just going to draw a couple of those, a couple of chlorines that are already in there because it's sodium chloride solution. Now let's say this silver chloride starts to dissolve. One of the silvers breaks apart from the chlorine. And then maybe another silver breaks apart from another chlorine, but then we reach the maximum amount of chlorines that we can have. We are in a saturated solution. Well, let's think about the concentration of silver. The concentration of silver is the moles of silver divided by the volume. Now the volume here is half as much, and it's twice as much right there. Even though in my drawings the amount of silver is the same, there's 2 silver atoms and there's 2 silver atoms. But this is 2 silver in a smaller volume, and this is 2 silver in a bigger volume. So the concentration of silver is greater in beaker X, and it's less than beaker Y. Greater. Okay, nice. That one's 19. And now we're on to the free response. Okay. Write the equation for the dissociation of silver solid. So we have AgCl solid, and it's going to break apart the dissociation of silver. So it's going to break apart into a silver ion and a chlorine ion, but it's dissolved in water, so these are aqueous. So there's my equation. Calculate the concentration of silver in that saturated solution of silver chloride. Now, if I were to write a KSP expression for this, it'd be the concentration of silver times by the concentration of chlorine. They'd both be raised to the first because there's coefficients of 1. Don't forget that we have molar solubility. Whenever there's a coefficient of 1, we can replace concentration with just S. So this would become S times by S, or S squared. So KSP is equal to S squared. Now, the concentration of silver is S. So if we can solve for S, then we have our answer. If I take the square root of KSP, this will equal S, which is the concentration of the silver. KSP, it gave it to us right up here. So the KSP is 1.8 times by 10 to the negative 10. 1.8 times by 10 raised to the negative 10, and then I'm going to take the square root of that. And then we don't have to write it in scientific notation, but I'm going to 1.3 times by 10 to the negative 5th molarity. Okay, there's our concentration of silver right there. Explain why chlorine solid is less soluble in seawater than it is in distilled water. Well, seawater has salt in it, and table salt, right? Like it's not, yeah, sodium chloride. And sodium chloride contains a common ion, which is chlorine. So we see this concentration of this chlorine. So why is silver chloride less soluble in seawater than distilled water? And it's because seawater has a common ion, which is chlorine, and whenever there's a common ion present, then an ionic compound is less soluble. Okay, so again, that would be my explanation here. It'd be when there's a common ion in the solution, then what we're trying to dissolve becomes less soluble. Okay, in this case, because seawater contains chlorine ions, it makes it so that the silver chloride, which also contains chlorine ions, is not able to dissolve as much. Something along those lines. Great. Now, on to 21. A student draws a particulate diagram shown to represent the ions present in an aqueous solution of strontium hydroxide. Water molecules are intentionally omitted. Identify the error in the student's drawing. The most common error is not made, which I'm happy about. They left the little hydroxides together. They didn't break it apart into oxygen and hydrogen. However, when solid strontium hydroxide breaks apart, for every one strontium, there's 2 hydroxides, and I think that's what we've got wrong here. That I see if I have 1, 2, 3, 4 strontium and 4 hydroxides. And so it would need to either be this, 2 strontiums to 4 hydroxides, or 4 strontium to 8 hydroxides. So we had the wrong ratio of ions. For every 4 strontium 2+ ions, there would need to be 8 hydroxide ions, something like that. Great. Part B. The student prepares a saturated solution by adding excess strontium hydroxide to distilled water and stirring until no more solid dissolves, so it's saturated. The student determines that the concentration of strontium is this. Calculate the concentration of hydroxide. Okay, so kind of like we said, for every strontium, which is 0.043 molar, there's going to be twice as much hydroxide. Like if strontium, which there's only one of them, if it has a concentration of S, the molar solubility, then the concentration of hydroxide, because it has the coefficient of 2 in front of it, it's going to have twice the concentration. It's going to be 2S. So that means its concentration is 0.086 molarity. And then now we need to calculate the value of KSP. This can be done one of 2 ways. It tells you that the KSP is the concentration of strontium multiplied by the concentration of hydroxide squared. So you could do this value times by this squared value, or you can do KSP is equal to 4S cubed, where that is our S value. Either way is fine. Get the same answer. 4 times by 0.043 cubed. And then that's going to be 3.1, I guess I need to round that to 3.2 times by 10 to the -4. Okay, nice. The student prepares a second saturated solution of strontium hydroxide in aqueous 0.1 molar strontium nitrate. So the first thing I'm noticing is we're trying to dissolve strontium hydroxide in strontium nitrate, so there's a common ion, which is the strontium. So this is going to dissolve less because the solution has a common ion. Will the value of hydroxide in the second solution be greater than, less than, or equal to the value in the first solution? The concentration of hydroxide will be less. Okay, and the reason why it will be less is because less strontium hydroxide will dissolve due to the presence of the common ion. So what I wrote was the concentration of hydroxide will be less because less strontium hydroxide will dissolve due to the presence of the common strontium 2+ ion. Okay, if 3.2 grams of O2 is consumed in the reaction with excess nitrogen monoxide, how many moles of NO2 are produced? All right. This one is just goalpost. Yeah, because see how they give us one starting amount, and then we're solving for one ending thing. So we're starting with grams of O2, and we're going to go to moles of O2, because then we want to transition to what we end with, which is moles of NO2. So here, grams of O2, moles of O2, moles of NO2. We're starting with the 3.2 grams. Now, grams over moles coming from our periodic table. There's 2 oxygens, so we should get 16 grams. Or sorry, it's double that because it's 2 of them, so it's 32 grams per mole. And then when it's moles over moles, it comes from the balanced equation. And for every 1 O2, it looks like there's 2 NO2s. So then 3.2 times by 2 divided by 32. 204.8, but I'm starting with 2 significant figures, so this would be 2.0 times by 10 to the second moles of NO2. Okay. Yeah, I'm a little hesitant because of the double arrow, but I don't see, they don't give you a k-value or any other way to use an ICE table on this. So yeah. Which element is oxidized in the reaction? So we have 2NO plus O2 turns into 2NO2. Okay. We give oxygens a -2 oxidation number. And then because NO was neutral, it wasn't plus or minus anything, that means that the nitrogen had to have been a +2. Now there's a few times where O2 does not, where oxygen doesn't get a -2 as its oxidation number, and one is when it's in its pure elemental form, and it gets a 0. Peroxides, we don't have one, but like something 2, oxygen 2, that's the rare times that oxygens are -1s and the other things are +1s, but we don't have one of those. So then for nitrogen dioxide, each of these oxygens are a -2. There's 2 of them, they're each -2. So this single nitrogen has to have an oxidation number of +4. Now, Leo the lion says grr, right? Losing electrons is oxidizing, gaining electrons is reducing, and we're trying to figure out which element is oxidizing. So we see that nitrogen goes from a +2 to a +4. This is losing negative electrons, so that's the guy oxidizing. So which element is oxidized? Nitrogen is oxidized. justify your answer in terms of oxidation number. Nitrogen went from a +2 oxidation number to a +4. Great. So nitrogen is oxidized. Nitrogen went from a +2 oxidation number to a +4. The partial pressures of the gases in the container are monitored at constant temperature and recorded in the table below. Now, before we go on to the questions for these, I want to point out a couple of things. First, the amount of NO is decreasing because its pressure is decreasing. The amount of O2 is also decreasing, and the amount of NO2 is increasing until we get to ×7. Then it stopped going down and it stopped going up. So we must have reached equilibrium. So this must have been equilibrium. And then getting up to this point though, NO and O2 are reactants where NO2 is a product. So if the amount of NO and the amount of O2 are going down, and this guy's going up, then we must be favoring the forward reaction. We're not at equilibrium, we're favoring the forward reaction until we got to equilibrium. All right, so let's see what questions they have for us. At time 3, is the rate of the forward reaction greater than, less than, or equal to the rate of the reverse reaction? So at time 3, we're not at equilibrium. We are favoring the forward reaction. And so at time 3, is the rate of the forward reaction greater than, less than, or equal? Greater than. Reactants are decreasing and products are increasing. So the forward reaction is being favored. Okay. Part D. At equilibrium, the container holds the most molecules of which gas? At this equilibrium, the pressure of O2 is the greatest. That's because it has more O2 gas particles. So at equilibrium, the container holds the most molecules of O2. And then the reason why is the pressure of O2 is the greatest at equilibrium. Okay, that would mean more gas particles. Using the data in the table, determine the value of the equilibrium constant Kp for the reaction represented by the following equation. All right, so we know our Kp expression is products over reactants, so we have the pressure, because it's a Kp, not a Kc for concentration. The pressure of O2 in parentheses, not brackets, they're real sticklers about that. Pressure of NO2 in parentheses and not brackets over the pressure of NO. However, NO has a coefficient of 2, so I'm going to raise that to the second, and NO2 also has a coefficient of 2. Now, when it's a K expression, these are the pressures at equilibrium, but luckily from that table, we know that the pressure of O2 is 0.75 at equilibrium, and then the other ones are 0.5. So we get 0.75 times by 0.05. Did I say that? But it was 0.50. Yeah, it was. Okay. 0.5 squared divided by 0.5 squared. So obviously this 0.5 squared and 0.5 squared gets canceled, and Kp is equal to 0.75. Using the value determined in part E, determine the value of Kp prime for the equation below. All right, now a couple ways of doing this. Kp prime is going to equal products over reactants again. So we have pressure of NO, pressure of O2 over pressure of NO2. And then you can go and you can, oh, and that guy's squared. You can plug this in again. You can do, I'm sorry, I'm just trying to see. Oh, y'all. Products over reactants, but then I didn't write it that way on this first one. Like, why is it not flipped? So, okay. Kp is going to be products, so the pressure of NO2 squared over reactants, which is pressure of NO squared over the pressure of O2. Great. Now, 0.50 squared divided by 0.50 squared times by 0.75. This is equal to 1.3 repeating. Those values are too sig figs, so I actually should probably say Kp is equal to 1.3. Now, we can treat it the same here, where this is going to be 0.50 squared times by 0.75 divided by 0.50 squared, and you'll get this Kp prime is equal to 0.75. That's fine. Or if you recognize that from this reaction in part E to part F, the only difference was it's the reverse equation. So whenever we reverse an equation, you just do the inverse of the K value. And so if we grab that, if we do 1 divided by that original K value, we will get 0.75. So either way, we'll get 0.75. And then the last part, which gas, nitrogen dioxide or O2 gas, will behave most like an ideal gas at low temperatures? So we're not talking about difference in temperature or different in pressure. So the only difference could be IMFs. Nitrogen dioxide, I'm seeing if it's polar or nonpolar. MC1, 2. And can nitrogen have an expanded octet? No, it can't. Okay, I'm gonna grab a pencil for a second. Okay, so here's where I'm starting, but I'm going to grab this free radical and that free radical, and I'm going to turn those into a bonded pair. And so then this guy's happy, 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen's good. It's in period 2, and only 3 through 7 are large enough for an expanded octet. So does this guy just have like a free radical somewhere? That's usually why it's like an NO2 minus, huh? Because I usually gain one right there. Okay. And then O2 is symmetrical, it's nonpolar. So the IMFs will definitely be stronger for this guy than that one. So which gas, NO2 or O2, will behave most like an ideal gas? O2. Okay. Justify your choice. The IMFs between O2 molecules are weaker or smaller than the IMFs of NO2. The weaker the IMF, the more ideal, or the weaker the IMF, the more ideal gas acts. I don't love that, but a gas will perform more like an ideal gas when its IMFs are weaker. Okay. Alrighty, good work. Done.